Okay, so after we went through basically those few theorems about rational numbers, so now let's see, basically let's go through a couple of examples. Let's see how we can actually use them. So for example, if you have some rational number like this number over here, like 13 by 3125. 3125. You have this rational number over here. You want to know whether this number will have a terminating or non-terminating. Basically, there can basically be two cases: whether terminating decimal expansion, okay, or the decimal expansion could be non-terminating, repeating. Okay, so now what we said was that if you have a basically the theorem that we had was that if you had a rational number in the form P by Q, where P and Q are co-primes, being co-prime, and that basically the factorization, the prime factorization of Q is in the form 2 raised to the power m times 5 raised to the power n, where m and n are some positive integers, then in that case basically the decimal expansion of x is basically non-terminating. I'm sorry, is going to be, I already forgot. See, for example, let's say that you have is of course terminating. And as an example, I can, as a counter, as some example, we said that, for example, 1 to 7, the decimal expansion of this number was non-terminating repeating. And the reason for that is that basically the denominator over here is not in this form. But if you have some number like, for example, like this number over here, you have some factors of 5 at least in here. So the decimal expansion of this number would be terminating, meaning that you could express your denominator in terms of 10, and then your basically the number would be terminating, meaning that and actually let's work on this one. Let's work on this one over here. 13 by which is basically, let's do it over here. So you have 13 by 3125, right? Now you see that basically, if you think of this as P by Q, over here P and Q are co-prime. P and Q are co-prime, and the reason for that is that basically I really don't know at this stage whether P and Q are co-prime. First, what I need to do is that first I need to prime factorize this number, see what sort of factors I have here, and then I can, of course, if for example, if there is a factor of 13 in here, I could cancel them out, and then the numerator will change. But otherwise, if P and Q, if I suppose that P and Q is co-prime, but basically the only thing that I need over here really is that this number over here, 3125, is some multiple of 5 because it's divisible by 5, and I can tell that because it ends with a 5. So you have at least one factor of 5 in here, so you can make some changes to the number, and then the number will have a terminating decimal representation. So what that means is that, what I can do in order to do that is that I can take this number and analyze this the denominator, meaning that prime factorize it. So if I write if I write 3125, let me write it down over here. If I write 3125, and if I divided this by 5, I would get 3125. Divide this by 5, I'm going to get 6 times 5 is equal to 30. 1, 2. 2 times 5 is equal to 10, 25, and then 5 times 5 is equal to 25, 0. So that's the same thing as 5 times 625. And I think 625 is 25 times 25. 25 times 25, so that is 25, 12, 0, 50, and that's 625. So 625 is the same thing as then 125 times 5. 5 times 125, and that's the same thing as 5 times 25, and that's the same thing as 5 times 5. So then 3125 is the same thing as 5 raised to the power 5. That's the same thing as 5 raised to the power 5. Okay, so 5 raised to the power 5 is equal to 3125. Okay, so then what I can do, there must be tools for doing this kind of thing, meaning prime factorizing and that kind of thing. And actually I do know about some of them, but I mean most of the time, whenever I'm doing mathematics, I enjoy basically playing with numbers, so I do that. Otherwise, for example, when I'm doing, sometimes I do, for example, I work on some physics problems or electronics or things like that. In those cases, I don't mess with numbers. I just enter them into some calculator and get some number out. Otherwise, if I'm playing with mathematics, I usually play with numbers, and it's actually quite interesting. So let me go and take a couple of minutes rest. I'll be back with you with the rest of this with this number. Okay, so so basically now you can see that you can write this number as 13 over 5 raised to the power 5 over 5 raised to the power 5. So, and you see that P and Q are basically they have no common factors. They are co-prime because this is, you have a 13 over here, and you have some factors of 5 over here. So basically these two numbers are co-prime. And if you have 5 factors of 5 over here, in order to get basically, you know that the 10 is equal to 2 times 5, meaning that 10 raised to the power meaning that 10 raised to the power 1 is equal to 2 times 5 raised to the power 1. And what that means is that 10 raised to the power 1 is equal to 2 raised to the power 1 times 5 raised to the power 1. Okay? So, if you want to get some factors of 10 in the denominator, and you already have 5 factors of 5 here, you need 5 factors of 2 as well, so that you can get some sort of situation like this going here. So so if I multiply this by 2 raised to the power 5 and multiply the numerator by the same thing, 2 raised to the power 5, then I will be able to express my denominator as 5 factors of 10. Okay, so now 2 raised to the power 5 is equal to, I think, 4 times 4 is equal to 16, 32. That's 32. So that's the same thing as 13 times 32 over so yeah, that's the same thing as 13 times 32 over 3125 times 32, and that's the same thing as and you don't really need to do this step. What you can do is that you can write this as 5 into 2 raised to the power 5, which is the same thing as 13 times 32 over 10 raised to the power 5. And 10 raised to the power 5 is simply 100,000. But now 32 times 13 is equal to 69032, and that's a 6, that's 11 1, and 100 basically 6 11 416 over basically 100,000, over 100,000, and that's the same thing as 0.00416. Okay, so that's basically that. So this number was actually and you can see that this number has a terminating decimal representation, right? Or let's say you have another number over here. So you have, for example, 17 over 8. This will have also a terminal representation because you can write this as 17 over 2 cube, and then you can add basically, you have 3 factors of 2 in here. You can add 5 factors of 3 factors of 5 as well, meaning that you can write it as 17 times 5 cube over 2 cube times 5 cube. And then you can write this as 5 cube is equal to 125, so 17 into 125 over this is 2 times 5 whole cube, which is equal to 17 times 125 over 10 cube, which is equal to 17 times 125 over 1,000. Now what is 125 times 17 is equal to 7 times 5 is equal to 35, 3, 7 times 2 is equal to 14, 17, 1, and that's an 8, 0, that's 125, and you have a 5 over here, 12, 1, and then you have 11, 1, 2, 1, 2, 5, 2, 1, 2, 5 over 1,000, which is equal to 2.125. It's a terminating decimal representation. And you can actually test this. For example, you can write 17 over 8, 2.125. Okay, it's actually pretty interesting, pretty powerful tool that you have over here. Without doing any sort of division, you can actually get to the number. Or let's say that you have 64 over 455. 64 over 455. So basically 64 is the same thing as is basically some factors of 2, right? It's some factors of 2, and 455 is some factors of 5. And I can tell you that this number is also has a terminating decimal representation. You want to see how that happens. So for example, let's go for 455. 455, if you divide it by 5, you will get 9 times 5 is equal to 45, and 1 times 5 is equal to 5, so that's 91. So that's 5 times 91, and 91 is the same thing as I think it's 8 times 8, right? 8 times 8 is no, I think 91 is a prime number, if I'm not wrong. Oh, 7 times 13. Okay, 7 times 13. So that's 7 times 13. So okay, so basically you can write this as 64 over 5 times 7 times 13, right? And now you see over here, you cannot do much over here, because the decimal representation of this number is not going to be terminating. The reason for that is that you have these factors of 7 and 13 over here, and these factors of 7 and 13, you cannot cancel them out with the numerator. So that's going to make the number, that's going to basically cause the number to have a non-terminating decimal representation. And if you want to see this, you can simply divide 64 by 455, and you see that the decimal representation is non-terminating. Now this number has been rounded off to, I don't know, 13, 14 decimal places. So what that means is that the denominator is supposed to have strictly factors of 2 and 5, and anything else if you have in the denominator, for example this 7 or this 13, if you can cancel them out with the numerator, you're fine. Then still you will have the terminating decimal representation. Otherwise, otherwise the decimal representation of the number is going to be non-terminating. Or for example, if you go for 15 over 1600, 15 over 1600. So this is going to be terminating, because you can write this as 15 over 16 times 100, right? And 16 is basically 4 times 4, so 2 raised to the power 2 raised to the power 4, I suppose. 2 raised to the power 4 is 4 times 4, which is equal to 16. So it's equal to 15 over 2 raised to the power 4 times 100. Okay, so what you can do here, is you already have 100 over here, so you don't have any problems with that. But you need, since you have 4 factors of 2 over here, you need 4 factors of 5 as well to make 4 factors of 10 here, right? So I'm going to write this as 15 times 5 raised to the power 4 over 2 raised to the power 4 times 100 times 5 raised to the power 4. So now 2 raised to the power 4 and 5 raised to the power 4 is the same, so you can write this as 15 into 5 raised to the power 4, and then 2 raised to the power 4 times 5 raised to the power 4 is 2 times 5 whole raised to the power 4 times 100. And that's the same thing as 15 times 5 raised to the power 4 over 10 raised to the power 4 times 100, and that's equal to 10,000. So 15 into 5 raised to the power 4, and that's equal to 10,000 times 100, which is equal to so this number over here is going to be equal to basically 10, that's 10,000, and 2 zeros over here, and this number over here is going to be equal to 5 raised to the power 4 is 625, and 625 times 15 is equal to 5 times 5 is equal to 25, 2, 10, 12, 1, 31, and that's 625. So you have 5, 7, 3, 9, 9375, 9375, and then your number is going to be equal to 36 decimal places, so 0.009375. And you can actually test this thing. 15 divided by 1600 is equal to 0.009375. Okay, so that's actually interesting. Or we could have a couple more examples here. For example, 29 by 343. 29 by 343. So the first thing that you want to do is basically see what sort of factors you have in the denominator. And it seems that this number is actually not going to have a terminating decimal representation, because you have a 29 in here, and 29 is a prime number. It's a prime number. It's a proven prime, right? So now the factors of 343 are, let's see, we need to know what sort of factors we have in here. So 343 is probably divisible by, I don't know. So 343 divided by 7, I think 34 minus 6 is equal to 28, so it's divisible by 7. It's divisible by 7, so 343 divided by 7 is going to be equal to 7 times 5, 7 times 4 is equal to 28. So that's 63 and 9. And so basically 343 is the same thing as 7 times 49, and that's 7 times 7. So you have 7 cube in the denominator. You have 7 cube in the denominator, so you can write this as 29 over 7 cube. And since you have 3 factors of 7 in here, the decimal representation of this number is going to be non-terminating. The reason for that being that, of course, there is no way to get rid of these factors in the denominator, and you cannot simplify them with the numerator, so the numbers are not going to be divided evenly. So then you get a whole bunch of numbers non-terminating in simply non-terminating decimal representation. So that is that. So for example 29 by 343 is equal to, you see, it has some sort of non-terminating decimal representation. Or if you have, for example, 23, or if you have, for example, something like 23 over 2 cubed times 5 squared. Okay, so this over here, you can make some changes to it. You have the only factors that you have in the denominator are factors of 2 and 5. But the problem is that you have 3 factors of 2 and 2 factors of 5. So what you want to do is that you want to write this as 23. You want to have the same number of factors of 2 and 5. So since you have 3 factors of 2, then you want to add a factor of 5 as well. So 5 raised to the power 2 times 5. And then multiply the 5 over here as well. So that's 115 over 2 cube times 5 cube, and that's equal to 115 over 10 cube, and that's equal to 115 over 1000, which is equal to 0.115. Okay, so that's basically how you do that. Or for example, let's say you have 129 over 2 squared times 5 raised to the power 7 times 7 raised to the power 5. Okay, so you have no problem with these two factors. These are 2's and 5's. You can somehow mix and match and make 10's out of these. But about the 7, you have to do, if the 7's can be somehow, which is of course not possible, if it was possible to cancel out the 7's with some factors in the numerator, then you would be fine, and this number would have a terminating decimal representation. Otherwise, as it is, it's not possible. You can still do something if you want to simplify your numbers. For example, if you have some number like this and you still want to get a whole number, not all of those, not to lose any precision in your number, what you can do is that use whatever you can use and take whatever you cannot use, just take it out and express it as a fraction. Meaning that, for example, here you have 129, and this is 1112. I think this is divisible by 3. So 129 divided by 3, you will get 4 times 3 is equal to 12, and 3 times 3 is 43. And 43 is divisible by nothing, I suppose. So 43 is, I think, a prime number. it's a prime number. Okay, so so what that means is that you can write your this number, you can write it as 3 times 43 over 2 squared times 5 raised to the power 7. And then, since this number is not going to help you much, you can take it out, times 7 raised to the power 5. And then what you can do, I mean, if it's necessary really, what you can do is that you can add 5 factors of 2 here. So 3 times 43 times 2 raised to the power 5 over 2 raised to the power 2 times 2 raised to the power 5 times 5 raised to the power 7 times 1 over 7 raised to the power 5. And then here you have 2 raised to the power 7 over here. So you have 3 times 43 times 2 raised to the power 5. And then this is 2 raised to the power 7 times 5 raised to the power 7 times 1 over 7 raised to the power 5. And this is the same thing as 3 times 43 times 2 raised to the power 5. And this is 10 raised to the power 7 times 1 over 7 raised to the power 5. And then you have this number over here, 2 raised to the power 5, I think it's 32. So that's 32 times 3. 32 times 3 is equal to 6. 96 times 43 is equal to 18, 1, 27, 28, 0, 24, 2, 36, 38, and then you have an 8 here, 12, 1, 11, 4, 1, 2, 8 is equal to 4, 1, 2, 8 over 10 raised to the power 7 times 1 over 7 raised to the power 7 raised to the power 5, for example. And then this is the same thing as 4128 over 10 million times 1 over 7 raised to the power 5. And then this is the same thing as you have 6 zeros over here, so you have 0.0670 zeros, I'm sorry, 7, so 4 plus 3, so 3 zeros, 4, 1, 2, 8 into 1 over, for example, 7 raised to the power 5. And 7 raised to the power 5, you can calculate whatever that is, doesn't matter, but now you got your number simplified as much as you wanted. So this is the decimal representation, and there is and this number basically is not a rounded number. It's the exact number. I mean, we have not rounded the number, we have not changed the we have not changed the precision of this number, and still simplified the number a little bit. Okay, but still the number but still there is no way to express this number fully in terms of a decimal representation. I just wanted to show you what you could do with the numbers. Or sometimes when you're doing something, then you want to solve a problem, sometimes you have to do these kinds of unstandard things to numbers so that you can get somewhere with your number. So the next thing that we have here is 6 over 15, for example. So you see that these two numbers are not co-prime, meaning that you can write this as 2 times 3, and you can write this as 3 times 5. So then if you can simplify these two, and this would be 2 over 5, and 2 over 5 has a terminating decimal representation, because you can write this as 2 times 2 over 5 times 2, which is equal to 5 over 10, which is equal to 0.4. Okay. Or if you have 35 over 50, for example. So, so there is no problem here, because this is the same thing as 35 over 5 times 10, and you can leave the 10 as it is. You don't have to do much over there. And then your 5, you just have to add a 2 here to get a 10. So 35 times 2 over 5 times 2 times 10, and that would be 70 over, that is a 10 times 10 is equal to 100, so that's 0.70. Okay. Or let me check this thing. 35 divided by 50.7. Or if you have 77 over 210. 77 over 210. So 210 is the same thing as 3 times 7. And then you can simplify the 7 with the 77 over here, and you will not be fine actually. Because 77 over 3 times 7 times 10, so this 10 is okay, and then this 7 can be simplified here, but then you will have a 3 over here, and this 3 you cannot eliminate it with anything, so this cannot have a terminating decimal representation. So that's basically how you work with these numbers. Or let's say that you have, let me see what sort of exercises we have here. Okay, so we have another question which is well, of course, which is also interesting, and we have a couple of numbers, like for example 43.123456789. 1, 2, 3, 4, 5, 6, 7, 8, 9, and also we have 43.123456789 repeating. Okay, and we have another number 0.1201200 12000 12000, and so on. Okay, so we said that basically if you have a rational number, and the decimal representation of that rational number is either terminating, or if it's terminating or non-terminating repeating, in these two cases your number is a rational number. Okay, if you have a rational number and the decimal representation of this number is non-terminating, non-repeating, then this is a irrational number. And this is an irrational number. Okay, so over here what you have is 43.123456789, and so this is a terminating decimal, then this number has a terminating decimal representation, so this is a rational number. This number over here has a terminating, has a non-terminating, basically has a non-terminating decimal representation, meaning that if you wrote this number, if you wrote this number down, it would actually be 43.123456789. Again, 123456789. Again, 123456789, and so on and so forth. So these basically 1, 2, 3, 4, 5, 6, 7, all the way through 9 is repeating itself over and over again. So this is again a rational number, meaning that you will get the same kind of remainders, and then the same block of number repeats itself in the quotient, and so that's actually a rational number. So that's basically that. Okay, so, and the example that we had for this number was 1/7. The example that we had for this number was, the example that we had for this kind of number was 1/7. We wrote out the decimal representation of this number, and this was 0.1428571, and the same thing again. So again 1428557, again 1428287, and so on and so forth. So this is a rational number, and of course you know it's a rational number because it was possible to express this number as a ratio of two integers, and the denominator is not 0. So you would write this number as 0.142857 repeating. Okay, so this is non-terminating repeating or recurring, so then it's a rational number. So then this is a rational number. But there are some real numbers like this one over here, and what this number is, you see, you have, first of all, it's non-terminating, and that's indicated by these 3 dots at the end of the number. So you have dot dot dot, meaning that it just keeps repeating and repeating, and it's non-terminating, and moreover it is non-repeating, meaning that you have 0.1201200120000120000, and so on and so forth. So you don't find a pattern over here, and also it does not terminate. So this is an irrational number. Okay, so that's basically that. So that's basically all that we wanted to, all that we have to discuss up to here. Now in the next videos we have a couple, I don't know what we have in the next videos. I'll see about that. So but whatever that might be, I'll see you in the next video. Thank you.